The problem that I think, the problem that I see some of you having, just to get going, is that we've got really two sets of information that have to be overlaid. If you can see how these two pieces of information are overlaid, that's 90% of the data. So the first piece of information is we have to identify where we are in the complex plane. And this is kind of a unitless picture of the plane. And it really comes just from the properties of the Mandelbrot set. So it's this is a hardwired fact about where the Mandelbrot set is. Right, so this is a unitless picture of the complex plane. And it's just a fact about the way that this set works that the interesting stuff is all near the origin. So there's really, it's kind of like Google Maps. You can zoom out to the global level where all of North America is about that big, right? And what does Los Angeles look like? It's like 1 pixel. Okay, great. That's a wonderful picture of Los Angeles, but if you want to see where you live, that's not nearly enough detail. So you have to zoom in 3, 4, 5, 6, 7 levels so that Los Angeles fills the screen. Then we can be a little more specific about where things are. So I think that was one mistake that I saw at least a couple of you made. The only part of the complex plane where anything is happening is this range right here. We do not need to look at this at a zoomed out level. There's nothing going on. And if you zoom out, all of the interesting detail is going to be 1 pixel in the center. So we're not going to have anything to look at. So zoom into something, have this region of the screen, you want that to fill the screen from about -2 to 2, -2 to 2. That's all we need. I can zoom out to 200, but there's nothing going on out there. So it's really kind of wasted space. There's any number of ways that you can document this and represent it in a program. I said define this thing called a Mandelbrot grid, just to keep up with all the parameters. But if you're in a hurry and you just want to try something out, you don't really have to define a formal grid, but you do have to represent these as variables. So I could say something like this. For the start one, you can either start in the positive direction or the negative direction. It doesn't really matter. Just remember which is which. Right, so those 4 parameters define where we are in the complex plane. Now completely separate from that, here's where we overlay that with the information that we need to actually create a grid of counts. So it's a completely independent decision how many points you want to divide this into. Right. So let's suppose I want to divide it into 101 points this way, 101 points this way. Now I pick some. It just turns out that the arithmetic, you come out with relatively nice round numbers if you pick some round number plus 1, because of the way we're going to, well, here's a quick example. Suppose I only want to divide it into, sorry, that's not right. Suppose I want a 3 by 3 grid. So I've got 9 points. Okay, so the number of columns is 3 and the number of rows is 3. One little calculation I'm going to have to do is calculate what the distance between the rows and the columns is in the complex plane. So I'm going to get that by taking this number, let's say take the width. The divided by the number of columns minus 1. Because there's 3 columns, but there's 2 intervals. And so I correct for that by doing a minus 1. So if I had picked a nice round number for width, and I pick a nice round number plus 1 for columns, dx comes out to be a nice round number also. It's really immaterial. This does not have to be a nice round number. It'll still work even if it's not. But that's just a little trick. If you pick for your number of columns, for your number of rows, some round number plus 1, you don't get really, you get easier numbers to print out, to document how big everything is. But it's not required. Okay, so I'm going to pick, I got to keep track of how many rows I've got, how many columns I've got. They should be the same number, otherwise you get a rectangular image. So, but that's, the choice that I make for how many rows and columns I want is independent of the size of the complex plane that I'm looking at. Pretty much once we pick these numbers, we're fixed. Those are going to remain that way. If we had time, an interesting thing to do would be to allow the user to click, drag, and release and zoom in on a portion of the Mandelbrot set, and that would cause all these numbers to change. But we're really not going to have time to do that.
Okay, that was the question. How would you know where the location is every time you click and drag? Because how would you find start X and start Y? Even if this is being zoomed out and
yeah, because this is, you're going to draw this on a panel or a canvas. Okay, and so there's an image. And you know the offset the offset of the image from the canvas in pixels.
Yes.
And then well, it kind of depends on how you define the mouse event. If the mouse event is relative, you have to keep track. If you define a mouse event relative to the image or a mouse event relative to the canvas,
okay,
you're going to, the delegate is going to tell you the XY coordinate of the mouse event in turn relative to either this origin or this origin. It just depends on how you set it up.
And then when you zoom again, the offsets are changed. You're not starting from 0, 0, and I mean.
Right. Well, step number 1 is you got to figure out where that. Let's say click, drag, and release. So I want that square right there to become my new image.
Okay.
Right, so I got to figure out where in the X. The number of divisions is going to remain the same.
Okay.
If you change that, you have to change that independently. So let's suppose I wanted 101 rows and 101 columns. Now, if I zoom in, it's still going to be 101 rows, 101 columns, except that image is now going to, the new square is going to define the whole image.
But how would you keep track of the start X and the start Y?
Right. So you know this point in terms of pixels. So you got to translate those pixels into the XY coordinates in the complex plane.
So you have to keep track of how many times you actually go through the zooming to know where isn't this going to get? Here's the thing that I think is going to happen. This thing, when you zoom it up, is gonna grow and it's gonna fill the whole image thing.
Right.
When it does that, then
you're going
0,
to change
0.
all of these values. You're going to change all of these values, and you're going to go back to your convergence test and redo them.
Okay.
Because you have a new region of the complex plane that you're looking at. I mean, my suggestion, going from -2 to 2, going from -2 to 2, that was just for starters.
Okay.
But once you've clicked, dragged, and released, you can calculate where in the complex plane that is.
Yes.
You have to translate from the pixel coordinates relative to either the image or the canvas. That's a minor difference.
Okay.
Well, let me do one more calculation, and I think it'll be, well, hold on.
It makes sense now.
Yeah, well, let's finish this calculation before we get to that question. So to be able to convert back and forth between where I am in my grid and where I am on the complex plane, I need to do that little dx dy calculation. So dx dy means within the complex plane, how far apart are my points? I need to know that number so I can calculate all the complex numbers that I would like to do the convergence on. So that one's easy. In the x direction, I've decided what the width is. So it's just the number of columns, this divided by the number of columns minus 1. That defines how far apart two columns are in units of the complex plane. And then in height, it's the same way. The height of the image, or the height of the region of the complex plane that I'm looking at, divided by rows minus 1. Okay, so now I can translate back and forth between pixels in my image and complex numbers in the complex plane, because I've got all the parameters I need.
Is there a division there?
Oh, yes. I said it, but I didn't put it in there. So now I can go back and forth. All right, so I create my array to represent my convergence counts. Now I'm in a loop. So now I'm in a loop over every point in that grid, defined by where I put the rows and the columns. So I just write a doubly nested for loop, where the outer loop counts the rows and the inner loop counts the columns. Okay, so right there is where I do a convergence test for a single point. And so according to the algorithm, Z starts off at 0, and C starts off at whatever point is represented by the grid position I'm at right now. Okay, so C is a function. C is a function of ij. It is not this, though. It's not that simple. I'm not simply taking ij and converting that to a complex number. It is a function of ij, but that's why I calculated all of these values. So the I variable is allowing me to count down onto which row I'm on. The J variable, I'm counting across to see which column I'm on. But now you've got to look at that figure and see, you've got to convert from I and J to the complex number that I and J represent. So in the complex plane, that point right there is 0, 0. As far as I and J is concerned, the upper left corner of my grid. But in the complex plane, what complex number is it?
-2, 2.
Yeah, it's minus, in the x direction it's -2, in the y direction it's +2i. So In other words, 0, 0 has got to convert to negative 2 plus 2i. Now what happens if I go one column over? So that's I is still 0 and j became 1. So what point is that? That's in the x direction, it's negative 2 minus, plus whatever dx is, plus 1 times dx plus 2i. Where's 0, 2? That's negative 2 plus 2 times dx plus 2i. What is 1, 1? That's negative 2 plus 1 times dx plus 2 minus 1 times dy. Right, so dx and dy are the key to translating between I and j in the complex plane. The complex plane origin is here. This is negative 2, 2. And so it's really just counting how many columns over in the x direction do you want to go, how many rows in the j direction down do you want to go. Right, so once I calculated that point, that becomes c. So let's calculate it out formally now. Okay, so I actually want to calculate the x value of this complex number c. So I know that I'm starting at negative 2, which symbolically is start x. And so start x is the negative 2 position in the x direction. Right? Now, based on which column it is, which variable tells me which column I'm in? Well, could, but my normal assumption is I'm going to let I count the rows and let j count the columns. So it's whatever j is. Whatever j is, that's how many columns over in the x direction I've gone in the complex plane. How much width do I associate with each column? dx. So it's start x plus j times dx. That's the x value for my complex number. Start x is negative 2. Right? Here's the y-axis. I'm negative 2 units to the left of the y-axis. That's my starting x position. As j increases, I move to the right by that many columns. So j times the width of one column added to wherever I started. That becomes the x-coordinate of the complex number at that position. So what about in the y direction? I just got to be a little careful here. You might wind up with an upside-down image, but you can correct it if you get it upside down. Actually, I think it's symmetric. We may not be, for this image, we may not know if it's upside down or not. It'll work either way. So I'm starting at positive 2. And I'm going to count down. So positive 2 in the y direction is up here. And all of these points, for the y value of that point, I want to know how many rows down into the grid I've gone. Well, that's I. I counts the rows. How tall is each row? dy. So that's the complex number. Now I can create it. Right, so we figured out which complex number it is by just counting rows and columns. How far away from the starting point is that row and column? Now, do the Mandelbrot convergence test for that value of c, that value of z. And that'll take another loop here. So by the time we're done, we have 3 loops. You have to loop over all the rows. You have to loop over all the columns. But as a result of those 2 loops, you've really just picked one point to do the convergence check on. Every combination of I and j picks one complex point to do a convergence check on. That requires a 3rd loop. So it's a triply nested loop by the time we're done. When you're finished, you have a count that represents, did that particular point converge or diverge? I guess the most correct way to say it is, did that point diverge or fail to diverge? We don't really know if it converged, we're stopping, we're giving up after 100 iterations. If it didn't diverge after 100 iterations, we assume, well, it failed to diverge, so we're going to call that a converge.
How would you know which one would be brighter and which one would be darker if we're always going to get to that max iteration every time?
Oh, you have an if-else. If it diverges, you're never going to you won't ever make it to the maximum divergence.
Yeah.
That causes you to break out of the loop and you have some number less than the maximum count. That becomes the count for that point, and that's a diverge.
If it converges, then we
check. And if it converges, that means you made it all the way to the end, and you look at the count is always going to be whatever max iterations is. But the convention to the figure is, if it made it all the way to the end, count is equal to 100, right? Reset it to 0, because the points that converge are painted black in the typical drawing of this thing. Okay, we'll go over that in detail in just a moment. But this is the basic structure. You need two loops to loop over all the points that you want in your image. And so that's flexible. How detailed an image do you want? For the main picture of the set, these numbers don't need to be changed. Just set them and leave them. But based on the resolution of the image that you want, you pick more or fewer rows and columns. When you're testing it for the sort of an ASCII version of the counts, you don't want it any bigger than that. But that would not make a great image because it's not enough resolution. But this is about the size that you want to check that the convergence tests are working. Once that's working, go back and set this to a couple of thousand. So you get like a megapixel image. But just for looking at the raw counts, keep it small. Yeah.
How does the image change if you increase max iteration?
How does the image change if you increase max iterations? It's actually dependent on which part of the set you've zoomed in on. And I really can't give a short answer. I'm not sure I can even give you a long answer. What I think is going on is, for this part of the image, it's not really that sensitive. If it were 100 or 200 or 80, you'd still get kind of the same image, because you're looking at the global image, and it's just a global property of the set that there's only so much detail you can get out. But when you start zooming in, you have to increase it, because at those higher zoom levels, if you make the iteration count too small, you don't see the detail. So you can't properly tell the difference between points that converge and points that diverge if the maximum count is 100. It's almost like you've introduced a blurring effect. So for the higher zoom levels, you do have to increase it, but I can't give you a formula. You just have to experiment. That looks muddy. Let's increase it. Maybe I'll get more detail.
You can make it a function of how small it is in respect to the original.
Exactly. I just don't know what the precise function is, how much you increase it as you zoom in. As far as I know, it's a heuristic. I don't know that there's I don't remember finding a closed form expression that says use this. Somebody might have come up with one, but I don't know what it is. Okay, so all right. So these two loops are simply to go through every possible point that needs to be convergence checked. Now back to your question, what is the actual convergence check? Okay, so let's see if I can erase this. Okay, so we always start off with z at 0, and c is the point that we're testing. So this varies. This is a function of I and j. So by the time we're done, this point will have swept over every possible point in the grid. That's the point of the loops. So if we zoom in on any one point, okay, the equation that we're using, Right, so in complex arithmetic, you take, you calculate z squared plus c, and that becomes the new value of z. Every time you are able to execute that, you increment your count of iterations. Right. Now, it's a fact about complex numbers. It's actually similar to real numbers. If you take a number that is small, meaning in the complex plane that means, it's got both a magnitude, a modulus, and a direction. So let's say it's that point right there where approximately that's the unit circle. So what's going to happen to that complex number if I square it? I can't predict easily what the direction will be, but I can tell you that the modulus is going to remain small. It's going to, I guess it's going to get smaller, just like a real number. Roughly speaking, it's going to bounce around a bit, but it's never, if I square it 10 times, 100 times, whatever, it's going to remain a small number. The direction will change, but the modulus never gets very big. So after 100 iterations or so, I'm going to stop and say, I'm going to check the modulus, and I'll notice, did the modulus get bigger than 2 units? That is our kind of arbitrary test to see if it diverged. And if the complex number started off small, the answer is going to be, no, it never got that big. Because when you square a small number, it becomes an even smaller number. But what if the complex number started out outside of the unit circle? So suppose that is my initial value of c. What's going to happen when I square that? Is it going to get smaller? Bigger. No, it's going to get bigger. And it's going to get much bigger really quickly. In fact, the further away from the origin it is, I only have to square it like once. And it's clearly out of range. So the points that are not in the set, most of them, I will detect that they're not in the set really fast. Just a couple of iterations. Right, so every time through the loop, there's 2 things that can cause me to stop the loop. Either I have exceeded the maximum number of iterations, in which case it must have converged, because I squared the heck out of it, and it never diverged. Other thing that could happen is, after just a couple of iterations, that number is already too big. It's already diverged, and I can stop. So if I've exceeded the maximum number of iterations, or the modulus is too big, either of those cases I break. No, stop. Okay, so that takes me to here. Now I have an if statement. If iterations greater than or equal to max iterations, that means it converged. I made it all the way through. I squared it again, and I squared it again, and I squared it again, and I squared it again. And the modulus now became too big. Not max iterations. Because in all of these images, 0 is used to represent points that are in the set. So it converged. Technically, the number of iterations was 100. But I'm going to reset it to 0 here, because that's the way I represent points that converge. I don't want to use the number 100 in that case. I just want to set that to 0. In the else case, though, the number I want to preserve is however many iterations I used. So whatever that count is, that's the number that I'm going to preserve. That number is going to be a number from 0 to 100. That means it's in the set. If I see something other than a 0, I actually know 2 things about it. First, it's not in the set, and more specifically, the count tells me how many iterations it took me to figure out it's not in the set. That's where the interesting thing about the set comes from. Back to the picture. If I look at the set in terms of counts, these numbers, these complex numbers that are a long way from the origin, all the counts are 1. What does that tell me? It only took me one time through the loop to cause them to blow up. They were already big, and I only had to square them one time to figure out, divergence. So you're going to see a bunch of 1s away from the origin. But as you get closer and closer to this little center, you get some really interesting counts. So all the interesting counts are right around the border of the figure. And that is essentially Mandelbrot's discovery, that the border is very interesting. The more you zoom in, the more detail there appears to be. So if max count is 100, if you zoom in enough here, what you're going to find is there's going to be a lot of counts that are like 99s. Very large numbers right around the boundary. So what that's telling you is whatever is going on there, it's very subtle. The difference between being in the set and being out of the set, you've got to be very careful to tell the difference between them. In fact, you might have to increase max iteration count to distinguish correctly between which side of the border those points are on. Now, if we zoom out enough, it doesn't really matter too much, right? If we're close to the border, close is good enough. We'll get the general idea. But the more and more I zoom in, the larger, back to your question, the larger the max iteration count needs to be, because the difference between being in the set and being out of the set is actually subtle. And that's where the interesting shapes come in.
Is the difference exponential in a way?
I don't know.
Oh.
Yeah, that's a good question. I don't know what the complexity is. That's out of my... Yeah, that's outside of my math knowledge. So let's go to the C# code that will generate just that much. All right, so here's a piece of code that I use it to define this Mandelbrot grid. You don't really have, it was just my suggestion that you define this grid using those parameters, because then it's easy to keep, because you want to keep track of them all together as a unit. And if you change one item, you don't want to get lost as to where you are, right? And so I have this method, you can organize it however, set params, where I give the starting point for the x and the y, the width and the height, the number of columns, the number of rows, or this number